Thanks, Tom, and thank you everyone for attending to the seminar today and just hear about my talk. So in this presentation, I'm going to explain and introduce the 3 papers that covered my PhD research, and that is covering the topics of using spiking neural networks for visual place recognition. You can find our code in this repository that are linked here, and send me emails if you have any ideas, suggestions, or potentially for collaboration. So the idea about doing this research ultimately is to have robots operating, whether it would be in delivery robot sending food to your home, or a drone robot monitoring the space, or an underwater robot operating in underwater, mapping an environment, whether it be a robot operating in a forest environment. In all of these cases, we would like a robot to autonomously navigate large environments, large real-world environments. And a part of navigation, as a part of navigation for these scenarios, we can use visual information. So using visual information to recognize the places that we've seen before. And if we can use algorithms that are super efficient in doing this navigation task, then we can operate for much longer duration. And that, in some cases, can also determine the success of a mission, or whether it be a failure or success is determined by how long we can operate on this. So our research is inspired by how animals, especially those with tiny brains, can navigate large spaces and find their way back home. For example, ants are only a few centimeters or less, and they can navigate, leave their nest, and travel hundreds of meters and find their way back home. And that's an incredible ability that we would like to get inspired from. So why is it applicable? For example, in many cases, like a space, like a Mars rover operating in Mars, we wouldn't have any other signals like GPS to navigate. And if we can use visual place recognition to visually recognize the places that the robot has seen, then we can use that information for mapping, so simultaneous localization. So what is the visual place recognition task? The task is the robot goes through an environment one time, records images of those environments, and that is called the reference set. And given a query set, so that's the amount of time that we come into the same environment, are we able to find the corresponding image from the reference set, even though it may look completely different. So what are the challenges? So for example, I can express next. So for example, we can be visiting the same place at different seasons, different time of the day, different illumination conditions. So it's just going to have a huge impact on the feature space of those images. And that is some of the challenges of this task. We can also have viewpoint changes. So for example, you might be looking at the same place from this direction or this direction, and it would just, the feature space would look completely different, but you would have to be able to identify that. So in extreme cases, depending on how you use this task, maybe you need the system to be able to identify the same place from 180 degrees, difference. If you're just looking at it this way, or if you're coming from that way, you would have to identify that is the place that you've been before. And some of the downstream tasks, that's a visual relocalization that I was talking about, or we can use that for online SLAM. So as the robot is trying to map a new environment and localizing itself, it will be able to use visual place recognition as a loop closure detection algorithm. Because if you're relying on other sensors to, for example, for this simultaneous localization and mapping, then maybe we would experience drift, and we can use this visual place recognition system to close the loops. So now that we covered some of the background information, I'm just going to explain some of the literature review that would be useful in understanding why we did what we did in the works that I'm going to be presenting. So I talked about spiking. I said that we're using the spiking neural networks for this task, and excuse me, this spiking neural networks are part of the neuromorphic computing field. So in this field, we are trying to closely mimic how the neurons, for example, in our brains operate, so that we can use the high energy efficiency of those models and replicate that for example, for other tasks, like for example, for robotics, that would be super useful. And to do that, I just wanted to cover what the actual biological spiking neurons have, the different components, and how they transfer information. So these spiking neurons transfer information using action potential or spikes. So when there is a change, for example, in the scene, and that's what a lot of like the event cameras, which a number of people here I know use, also know about. So if there's a change in the scene, then it's a 1, otherwise it's a 0. So that's a spike or an action potential. And we have the presynaptic neuron is the neuron that is sending the information, and the postsynaptic neuron is the neuron that is receiving the information. And in these spiking neurons, we have the input, so these are the dendrites, and then the outputs, which are the axons. So basic stuff, and then the synapse is very much like a DNN. That's a connection all the way between two neurons. So in DNNs, we model a neuron using, for example, a railroad function or something like that. And in the spiking neuron, we model the neuronal dynamics of a spiking neuron, and that is its internal voltage. And when it receives an input spikes, its internal voltage is going to increase, and then it's going to decay exponentially. And if it receives multiple input spikes at a short interval of time, then its voltage is going to increase and increase. And then if it hits a threshold, then that's the time it's going to send an output. So this sort of like, it's like a memory of information. And as soon as it is sure enough that it has received enough information, then it's going to send that information to its output. So that's one way of modeling these neurons, which I have used here. And then we learn using spike time dependent plasticity. So this is also a biologically inspired learning algorithm that is unsupervised. So we look at the timing of the spikes from the presynaptic neuron to the postsynaptic neuron. So that's basically two neurons in two different layers. If one has spiked before or after the other, then that affects how much change the weight between these two neurons are going to be. So if the presynaptic neuron keeps on firing before the postsynaptic neuron, then we know that's the information that is being passed through. So the weight is going to keep on increasing. The change in weight is going to keep on increasing. And otherwise, it's just, if that's the other way, then it's going to keep on decreasing. The saying that inspired this learning algorithm is the neurons that fire together, wire together, right? So if these neurons keep on passing information, then we know that there is a correlation. Otherwise, it's not correlation. So they don't correlate that. Some of the information that might be useful. So how SNNs differ with DNNs. So in current computing algorithms, we pass information, so continuous value information, and DNNs pass through continuous value information as well, the outputs, whereas in SNNs, the information is very sparse. For example, we can think of it as reporting only changes in the scene, for example, about the place, and the output is also sparse out, which also helps with the energy efficiency. Although SNNs seem to be really useful, they're not as developed as DNNs. So we have lots of tools in DNNs, for example, PyTorch, that would help us like build a network as fast as possible. But with SNNs, the tools are really sparse and disconnected. So that is something that a lot of people have been working on improving. Another important component that would be useful to use for robotic tasks is neuromorphic hardware. And that is replicating how our brains work in hardware level. So as opposed to CPUs and GPUs that also need processing for example, weights that are always zero, then we get neuromorphic hardware removes that requirement. So it only processes changes as well. And how we achieve this high energy efficiency is through multiple key differences in this hardware that we don't have in normal GPUs and CPUs. So for example, we have integrated processing and memory in this neuromorphic hardware. So the data delivery between the memory and processing is really minimal. We have sparse and asynchronous event-based data because we're only processing changes in the scene, then we're not, for example, processing pixel values that are always going to be constant, right? So that's why it's going to decrease the amount of computation significantly. Because the neurons are modeled using their internal voltages, we have parallelization abilities at very low level because all of these neurons can process information simultaneously. So that's a lot of fine-grained parallelization that would lead to this incredible ability of gaining those high energy efficiencies and having low latencies. And these are some of the examples of hardware that are available for researchers. So at commercial level, we do have the company, I think, BrainChip, that is operating based on here in Sydney, actually. But they're doing some work as well, but the tools are not as advanced yet. So we've been collaborating with Intel to deploy our networks on their neuromorphic hardware, but there's been some challenges in terms of software. And I was talking earlier with you guys, and like we can't even do division in some cases, so we just have to find other ways of doing that. Another important component that was important for these works was to be able to scale our models to learn places in a large environment. So, for example, being able to increase the size of an individual network is not feasible, which we will see later on. And one way to deal with that would be modularity. So this concept has been used very commonly in classical machine learning techniques. And in this way, for example, we use a module that is a small size, and it only is assigned to learn a subset of places. So that reduces the amount of training time, for example, to train for large environments and be able to cover that large environment with modularity. So at test time, we feed the same input to all modules, and all of them contribute towards prediction. And if you look at it this way, it allows us, for example, if one module is learning all of the places that are within our center, which is the map we see here, then if we have more modules, we're going to cover more and more areas of the city, then we'll be able to do visual place recognition at city scale. So other works have used, for example, modularity in other ways. For example, they've tried to chop off the input image into 4 portions, and each portion is learned by a module. So that's one way to use modularity. Modularity and ensembling maybe have been used interchangeably in literature. People use them to refer to all sort of stuff. But one way that we've defined it in these works is to have duplicated models. I know it's redundant, it's more energy usage, but then our argument is that if we are moving towards deployment on neuromorphic hardware, then we wouldn't come across so much energy usage because of the high efficiency of these networks. So what we're going to have is that the same input is fed through multiple networks. And in classical settings for ensembling is that if you have multiple agents that are agreeing to the same prediction, then that is a high certainty, then as opposed to having one person saying that. And we've seen works, for example, on uncertainty estimation, where people have used ensembling like this to estimate the uncertainty of prediction. And this is a work that my supervisor, Tobias, Toby and Michael worked on using ensemble to for place recognition using event-based data. Another component that is popular for visual place recognition is that we know that for visual place recognition, we have this, usually we have this task where the robot is moving through an environment. So the information is that the inherent information between these images is that we have temporal information. We know that if I was here and if the robot was not kidnapped, then I would be here next, right? So we can use this past information for prediction. And that actually improves the robustness of the system to high illumination changes, for example. And that is something that we've used in this thesis as well. So for example, this is the distance matrix for the predictions of each query to all the reference images. Ideally, you want the darkest predictions corresponding to the correct matches to all lie along the diagonal because they have perfect one-to-one correspondence. And if we use sequence matching like that, you're basically convolving this matrix with an identity matrix. That's what it's really doing. It's forcing all of the diagonals to be increased, and that's what leads to sequence matching. So the idea of using spiking neural networks, neuromorphic computing for visual face recognition, ever since I started my work, have been increasing. You know, other people have been doing that. So this paper came out last year on in Science Robotics on using spiking neural networks and running that on neuromorphic hardware. So they ran it on the Titan chip, and it is taking multiple different kinds of sensory inputs and processing that using different types of algorithms to do this task. And we also have another postdoc at our center, Adam, who's working on trying to make the kind of networks that I had been developing more efficient. So he was using temporal information on how to do this even more efficiently as well, which I'm going to talk about once I get to the networks. So now, looking at the first work that I did, this was from our first work on submitting it to IEEE round and presenting it at April 22. So what we used was that because we come from a robotics background, we didn't have a lot of knowledge in trying to come up with novel architectures using spiking neural networks. So the better way to get started was looking at what is available out there and whether we can use it for the task that we want to demonstrate it for. So we started with using a 3-layer SNN that was originally developed by Dyer and Cook back in 2015 for digit recognition. And in this network, the image, we just like we decrease the resolution of the image and then input the image by using its pixel intensity as the firing rate of the input neurons. So we have as many input neurons as the number of pixels in the image, which is not efficient, but that's like a good way to get started with. And then the input neurons are fully connected to the excitatory layer. That we read out the number of spikes from the excitatory layer, and the inhibitory layer is just there to act as a winner-takes-all mechanism. So once, for example, an excitatory neuron gets activated for an input image, the inhibitory neurons inhibit all other excitatory neurons from firing because we're using an unsupervised learning method. If you don't have that, then all of the neurons are going to keep on firing, and it's really hard to keep a balanced activity because otherwise you would have either no activity or all neurons activating at all times. So that's what the input image is, and then we use the neuron dynamics of leaky integrating fire to model the neurons, and then the unsupervised learning, the spike time dependent plasticity, which I was talking about earlier. So this is what the visually look like. So we pre-process an input image to make it 28 by 28 pixels, and then we patch normalize the image. The pixel intensity set the firing rates for the input neurons, and then this is at inference time when we pass through an image. The excitatory neuron that gets activated is the one that is that has the most activity, for example, and we read out the activity, and based on the activity of the excitatory neurons during training, we use that to say, oh, okay, so the group of neurons that were most active for this particular place probably have learned that place. So that's the direction we go for that. So in the original Dive and Cook model, how they assigned the neurons to have learned a place was that they look at the responses. The highest responding neurons correspond to have learned a particular label. And in this task, they originally started with 10 digits. So these are 10 distinct classes. And what we tried to do was to use the same network, but now we have 100 places. So we consider each place sampled at a particular interval, for example, a meter or two, as a different class. Excuse me. So there's a lot of visual overlap between these classes. And what we're trying to do is basically template match. So what we tried to do instead was to consider the ambiguity in the neuronal responses. Sorry, for this prediction. So we came up with a weighted neuronal assignment. So in this way, we consider the ambiguity of the neurons. So for example, we have a neuron 3 during training that fired the spikes during training to 4 different labels like that. So at test time, when this neuron fires that many spikes, we're going to decrease its contribution because we know that it was so ambiguous during training. The other components of our weighted assignment is that if a neuron somewhat equally fired the spikes or was activated during training to 2 different labels, then we're going to divide it almost by half based on the sum of the spikes of the training if it fired at test time. Our last component is looking at, for example, if a neuron was firing really nicely for 2 different labels during training, but nothing for that 2 same places at test time, that we're just going to not consider it at test time. And when I was presenting it to my panel members in my thesis, one of the panel members said that this is really related to the information theory and how to try to find the entropy of information. Yeah, so very similar to that. So our weighted probability-based assignments, which comprise of these 3 components, which is the one in red, perform very comparably to conventional VPR techniques, net1 and SAT, and compared to the standard techniques, we much better. And this is like a sample of how the network works. So as we go through, we sample the images at a particular interval, and that's what the network sees, and that was the network. This is what the network sees at test time, and this is what the network was trained on. So as I mentioned earlier, we want to increase this. So we only learn 100 places, which is minimal, but maybe in some scenarios it would work. So if we want to increase the size of the network to learn more places, we need more neurons in the network to accommodate for that. And this ablation study tells us that if we just increase the number of neurons, at inference time, we're going to have a huge increase in the inference time. Just to process one image is going to take 7 seconds if you have 6,000 neurons, which makes it so infeasible for deployment. Another issue is that if you want to keep the same performance, high performance of about 90%, then the number for for increasing number of labels, for example, up to 200 neurons, we need more and more output neurons. That's going to be exponentially increasing as well. So that's not feasible to just increase the size of the network to accommodate for more places. So in our second work, we looked at a modular approach, and that's what I was describing earlier. Sorry, I may need some water here.
Well, you keep talking. Okay.
Okay.
Yeah.
I can use this.
Yeah.
So for increasing the number of places, our previous work looked at categorizing only 100 places, and in this work we try to use the same data set, and now we want to learn more places, around 2,700 in this case. So we took a modular approach. What we did was that, given this path, so very long path of the places that the robot has seen, for example, in this case, it was like one of the data sets was like a train ride, so a train track. We take a small region of the area and we feed those images to train on a small network. So that's the same network as the previous work that I was presenting. And then the neurons are assigned based on the highest activity during training to places, which was the standard assignments that I was talking about earlier. So we did that for all of the places in the environment. We end up having many modules. All of them have trained only a particular region of the environment. So at training time, all of these modules are independent and do not interact with each other. And then at test time, we feed a query image, and this query image is passed on to all of the networks in parallel. And then we look at the activity of the neurons, the response of the neurons at test time to do the prediction. Ideally, the maximum response of the neurons among all of these modules would determine the place that it has learned, but it's not so feasible because during training, all of these modules were independent, so we don't really have a global regularization. And I also said that we have an unsupervised training approach, so we really don't have a loss function to rely on anything. Yeah, challenging. So we designed a post-regularization, post-training global regularization. What we did was that we feed the images from the entire environment to each module after training. So we weren't training at all. And then we looked at the activity of the neurons to these places. These are only the reference images, and this was used for training. And then we detected which neurons have responded highly to many places, and we just removed them at inference time. So we just don't consider those neurons. So what happened was that compared to the previous work where we merely increased the number of neurons in the network to accommodate for more places, our modular approach was more feasible. In this work, we couldn't really train it for much longer because the simulation was difficult. It was just going on for days and days, and just that's the accuracy I got after so long. And then compared to conventional VPR techniques, we are doing somewhat comparably. Yeah. But then these techniques are looking at larger image sizes as well, aside from sum of absolute differences, or SAM, which is just looking at the pixel differences between the reference and query. So this is what the prediction looks like. So given a query image, we are matching to the reference image, even though these places have been taken at completely different times. But I think the patch normalization bit in the pre-processing steps helps a lot, because if you're looking at it, you're just basically doing place classification. So each place is a template, and we're just matching it to its template. Yeah. So now moving on to our third work. I was just talking to Don about this earlier. We submitted this at Truro, and we received 7 reviewers. Not to discourage you from submitting to Truro, but I think it's just basically they couldn't find people that have information about both disciplines, both the spiky neural nets and visual place recognition. But it was a nice experience. It is accepted now. Yes, which is great. So in here, we continued on. So this is evolved forward from our previous conference paper. And what we did was that we started off with that single spiky network that was learning a small region in the environment. Now we shuffled the images, so it's learning places that are really far apart. So this actually helps with learning, like what we see in deep learning. When you shuffle images, you see an improvement because these places are now more distinct. And then we have the standard modular SNN, which works well as is, but now we paired it with an ensemble. So all of these modular SNNs are now receiving the same input, but at a shuffled order, and the initial random weightings for the learned to be learned, the ways that are to be learned are also different. So we are starting off at a different position for learning to encourage all of these ensemble members to learn a little bit differently. But the surprising thing was that their performance was the same. Even though the images were like all sharpened, and it was not predicting the exact thing differently, but it just performance was very much similar. Given a query image, we feed the predictions of all. We take the predictions from all of these networks, and then we sum them up, and that becomes our ensemble of modular SNNs. So we try to add as many enhancements as possible to make to see how much improvement we can gain. And then we also included sequence matching, where we consider images not just from current place that we are, which is the single image matching, but then it's looking at the sequence of images of the past places that we have matched, and try to use that in temporal information as well. So the number of key enhancements that we've added to this work compared to the conference paper that I presented was that in that work, we used 2 reference sets to train our network. So the robot had moved through the environment actually twice, and that's what we used. We don't use any great training on these networks as well, so that's the only information that we use. And then we had 20% of our test data set used for calibrating our hyperparameters, which meant that we need correspondences between every place that were in the 2 reference traverses, as well as the calibration set, part of the query set that was used for calibration. So what we did here was that we removed the need for calibration by streamlining the process for our hyperparameter selection, so that we're using the same thing across all data sets. And then we use 1 reference set. We showed that even using 1 reference set is enough without any pre-training, of course, to train our network, and it was able to learn those places as we see in the test. And then we were removing that need meant that we can use the entire query data set for our tests, which makes it more practical, I hope, when you're deploying it in the real world. So this time we scaled up our work to even more places, because we wanted to show how much we can scale this network and still be able to get some performance, keeping in mind that this is basically doing template matching. So comparing to our state-of-the-art conventional VPR techniques, these are some of the key outcomes. So we're looking at the bars here. So the green one is the recall at 1, or the accuracy of our ensemble of modular SNN on a traverse that is spring. Sorry, this is This is average across all many data sets, 6 data sets. So what we see is that the performance was comparable to conventional VPR techniques, one of them being the generalized contrastive loss. So it's using a generalized contrastive loss for learning feature representations. And then mixed VPR cosplays are some of the more recent VPR techniques that are state of the art. Another key information in this plot is that with sequence matching, so if you're using the past 4 frames, 7 or 10 frames, then what we saw was that we're gaining more, we call it one improvement with our spiking networks. So in here, the red bar for our network is much taller than the other networks. We also evaluated against more VPR techniques, but then we see the same. We see the same conclusions. Yes, basically. We also deployed it on a robot. So what we did was that we deployed it on a robot that is, the network is running on CPU. So it traversed a 100-meter path in our office space. That is the same as the work that one of the other PhD students recorded. So he had a nice shot, and I didn't have enough time to record an image. So I'm saying that we used the same deployment setup and robot. So what we did was that we collected the reference images offline, and then we trained one modular SNN with 4 networks, each learning around 25 places. And then we trained the network, and then we did online inferencing. So the robot moved to the same environment, collecting images at around 1 hertz, and it was able to recognize the system. As seen before, it was very slow at processing, but that is what we try to show, that maybe it would be somewhat possible to improve this for some particular task. So we did multiple ablation studies. One of the ablation studies was looking at the contribution of different components of the network. So for example, increasing the size of the network, which was the first paper that I covered, wouldn't scale well at all. So that's the performance when we're looking at 27,000 places, which doesn't work at all. It's very hard to train for many epochs. And then for our modular SNN, this is a spring to winter set. So we are training our network on the spring dataset and then testing it on the winter where places may completely different. With our ensemble, we see around a 5% improvement in recall, and using sequence matching around 15% or something. If we include the modularity ensemble and sequence matching, we get around 2.5 times improvement compared to the modular SNN. So for sequence matching, we wanted to study the responsiveness of the different VPR techniques to sequence matching. And we came up with a correct match sparsity term. So this is looking at the prediction, the mean distances to next correct match. So for every place that I was trying to match, I'm looking at how many places apart were all of the correct matches in these techniques, and then I take the mean of that. So higher values generally correspond to lower performance, because if a network is perfect at recognizing every places, then it's going to have a mean correct match responsiveness of 1, because every place has been correctly matched, right? So there are no distances. But then if a place is really, if a system is really bad at doing place prediction, or the underlying data set that is trying to match is really difficult, then the correct places are going to be really far apart. And that gives us a hint about the performance of the network on that particular data set. And what we see is that our networks, which is the modular SNN in blue and the ensemble in green, have a higher ratio of its recall at 1 with no sequence matching, which is sequence length of 1, to its recall at 1 with sequence matching using 4 frames. And what we see is that it generally holds the same key outcomes generally holds across all data sets that we evaluated. And another thing is that generally, methods with high correct match sparsity have a higher ratio because they benefit from the temporal information they gain with sequence matching. But whereas if the performance of a network is nearly perfect, like mixed VPR down here, then it's just not going to gain any more performance gain using sequence matching. We also evaluated the effects of ensembling, and what we see is that our ensemble of modular SNN gains. So this is the mean, we call it one of the individual ensemble members, the modular SNNs. And if we use an ensemble of that, we're going to have an increased performance with ensemble of 3 or 5. Whereas the generalized contrastive loss network, which was the VPR technique that we compared it to, doesn't gain any very minimal performance over the individual performance of its ensemble members. And that will be because no matter where you start your initial random weights or how you shuffled your input images does not affect how the network reaches the final outcome. So that's what the network is good at. It's like, no matter where you start, you're going to end up with the same prediction, whereas our network wasn't doing that. So that's why it didn't benefit. GCL didn't benefit much from ensembling. APGEM is another technique that came out in like 2019. And what you see is that the different ensemble members have different performances, and the ensemble was actually worse, similar to or worse than the individual ensemble members. And that was because the networks here were actually different as well. So for example, one was using a resonant 50, one was using resonant 101. So the performances were vastly different, but the ensemble didn't actually do any better than the best performing ensemble member. So in summary, I covered 3 works. The first one was looking at using the spiky neural networks as an alternative approach for visual place recognition. And then second work was using a modularity technique to be able to increase the scalability of these networks to larger environments. And then thirdly, we wanted to see how far we can go with this if we add more enhancement techniques, and we try to make it as practical as possible. So for future works, lots of things to improve on. So one area is to be able to make these networks more invariant to viewpoints. At the moment, we are doing basically place matching, template matching. So if we can come up with an ability of representing these spaces in such a way that the model can tolerate viewpoint changes. So if I'm looking at this place from here or here, I will be able to say that I'm in the same place. That would be amazing. Currently, many conventional VPR techniques are really good at this. So this is the Tokyo 24/7 dataset, and some of the more recent VPR techniques, which are using transformers, have nearly reached perfect recall on these datasets. Of course, event cameras, which I saw in your lab as well, it's great to see. We can use event data to feed into spiking neural networks. And then we can also deploy it on neuromorphic hardware. So we have an entire pipeline of event-based information. And what it does is that because it's only processing changes from the sensing side to the learning algorithms based on the changes to processing them on hardware that is only processing changes in the scene, then we are gaining that high energy efficiency. Some early works that have used this neuromorphic pipeline have showed orders of magnitude improvement in energy efficiency and latency compared to conventional data sets. But of course, the tools are still improving, so it is difficult to show that or come up with that. But I think the potential is there for robotics tasks to be able to use neuromorphic computing for robotics tasks. to gain that high energy efficiency. And then being able to ultimately, of course, show that on robots as well, that it works on robots. All right, so that's everything I want to talk about. Thank you for listening.
All right, so for folks online, please type in the chat window if you have a question, and I'll ask you to speak up if you do. And locally, please put up your hand. Let's get it started. Yes, Nikolai.
Yeah, thank you for your talk. I was just wondering, so those spikes, let's say you are in an environment where you recognize a lot, or let's say that you recognize a lot all the time, and you get a lot of those spikes. So compared to just dense neural nets, let's say that you get like all of those spikes, would it still be efficient?
At the moment, no. It's right. This network that I'm using is using rate coding. So rate coding is not very efficient in coding the speeds because we are encoding pixel intensity and use that as the firing rate for the input neurons. And a more efficient approach, which one of the postdocs at our center had been looking at, was using temporal information. So encoding information using temporally, so that pixels with high intensity would fire first. So that's the kind, yeah. So that in that way, for encoding one pixel, we only use one spike. And if there's lots of changes in the scene, let it be. It's going to be no more than one spike for inputting one pixel into the network. Yeah, I mean, like that's something that I could have explored as well, but there was not a lot of time. I would say, yeah, but that's something that has been explored, and really a better way of encoding information. Yes.
Yeah, no, thanks for the talk. I guess I was curious, how would your model behave if you fed a query base that was never encountered before?
Yeah. Yeah, I mean, like I explored that at some point, but never get to a publication stage. What we see is that we can use all of that prediction for an uncertainty estimation. So the activity of the neurons that are most certain about the place, it tells us about whether we should trust it or not. So if we show it a place that it has never seen before, we expect to get low activity from many neurons that have never seen this before. So that would be a good indicator of saying that, oh, that's an unfamiliar place. Yes, yeah. But didn't explore that much, but that's how much I dig into it. Yes, yeah.
Thanks for the talk.
Yeah,
So I want to ask, is there enough resolution to be able to detect multiple objects in a scene in regards to like a spike?
Well, yes, there are other ways to create a network, a spiking neural network. What others have been looking at to get that higher resolution is to look at completely different types of networks. For example, you can develop an ANN that works really well and convert that to a spiking version. In that case scenario, the argument is that you can have a well-trained network that works really well, and then when you want to deploy it on a platform, then to gain that high energy efficiency, you just convert that to a spiking neural network. It's an approximation method to gain that high energy efficiency at inference. So that's how I go at it. People have done object detection using spiking neural networks like that. Yeah.
Got a question. So you, in your future work, you brought up the possibility of using some of this custom hardware designed to do spiking neural networks. Are there different camps of thought in how those are implemented? And is your work so far subscribing to one camp, or does everyone kind of agree what a hardware spiking neural network should look like?
There is no agreement.
Okay.
There is no agreement on what a hardware should look like or how it should operate. At the moment, a lot of people are trying to come up with frameworks that would work for multiple different types of neuromorphic hardware. Yeah, but for a long time, a lot of things have been disconnected. So that, for example, we have a lot of great advancements in neuromorphic hardware, and but then there's not a lot of communication with like creating the kind of algorithms that work well. So we have the algorithms that work well, but unfortunately, the capabilities are not possible to run on the particular hardware, or vice versa. And that's what's been a challenge, because there is no one uniting organization. But there is a bunch of organizations that have come through, like trying to do that thing, bringing researchers together from different components so that we can have those full neuromorphic pipelines. Yes.
Cool. And maybe a related question. So it all starts from inspiration from brains, right? So the human brain, animal brains, there's a lot of complexity in how they're signaling.
Yes.
And you mentioned excitatory and inhibitory connections, which are both present in the brain, but there's of course much more going on. But one thing that comes to mind is neural networks exist in a chemical bath that modulates their activity.
Yes.
So are folks investigating bringing more of these mechanisms into hardware or into simulated spiking neural networks, or is it more static and now it's a matter of making what we've got work well?
I don't know about that. At the moment, the focus for our research was making what we've got work well with place recognition. But that's a great question, because in neuroscience, a lot of things are actually unknown. We know that a lot of like processes for learning are happening chemically. And if you're just looking at electrical signals, that's not enough to tell you why these set of neurons are behaving the way they're behaving. So yeah, lots of work into trying to understand the black box and try to make that understandable, like what is happening in the brain. But of course, it's so much more complex than what it seems. Well, but it is complex, but it's very hard to tell. Yes. Yeah.
Yes. So you're using some sort of temporal structure to explore to improve the robustness.
Yes.
My question is, for your test time, if your car is starting in some middle point of the trajectory and walking backward direction, because the temporal structure is who comes first, and but now you are working in the backward direction. Can your model could be common, or how your model?
Then you would have to have an information about it going backwards as opposed to forwards. Then if you know that it's going backwards, then yes, we would be able to do that. Yeah, I think that would be possible. Yes, but then it wouldn't work if you place a robot from here and like manually take it to the other side. Yeah, that's a limitation with sequence matching.
Maybe time for one more question. If someone online has one, speak up, or locally. I'll bite if someone handed you a bag of gold and you went shopping. Do you know which existing hardware you would buy?
Existing hardware. For this task, you would have to think about, okay, how much development, and what are the current status of the hardware, and what are the available tools, for example, the software framework, and what can I do with it at this point. And then you need to collaborate with the people that are developing the hardware to be able to effectively deploy this. Yeah. It's a complex question. I mean, like I believe that with all of this hardware, you'd be able to do this task, but then it's just that there is not a lot of information about how to do it. And of course, as a PhD student, you wouldn't want to spend all time designing the functions, the low-level functions to do the basic tasks. Yeah. So if those are readily available, then that's something. But you want to look at, like, come backwards, like, what do I need and how can I get it? Yeah.
Very good. Well, Somayeh is going to be with us for another hour or so. If you have time, please come up and have a chat. Learn more about her work, tell her a bit about yours. But for now, please join me in thanking our speaker. Thank you very much, Somayeh.